Markov chain Monte Carlo, okay, and CNC. So I will start with an example, which I find very interesting, which is the following. So this is a sort of game you can do. So we start with a classic checkboard. And well, the classic checkboard has 64 squares, and the idea is to take cover this checkboard with dominoes. Okay, what is a domino? A domino is a rectangle of size 1 times 2. Okay. So this is a domino. Okay. So if I want to cover this rectangle with dominoes without overlapping, I need exactly 32 dominoes. So let's take an example. Okay. So I'm going to denote by this a domino. Okay. So we start like this, and we go on, maybe like this. I'm going to do it basically at random, I mean, in some way. But for example, when I put a domino here, this forces me to put a domino here, right? That's one restriction that we have. Okay. So if you're willing to, there is some combinatorics result that tells you that if you start like this and you always put a domino adjacent to these guys, and whenever you put a domino, we put all the other forced dominoes, this procedure will never get stuck into an impossible configuration. That will be the case if you start to mess around and put in dominoes in different parts of the board at the same time. Okay. So maybe I will do this and this. This forces me to do this and this, and I keep going on. Okay. Notice that this one forced me to do a lot of things. And as you can see, you always finish filling out the square with dominoes. Okay? So now, this model, this problem has been introduced by physicists, and they say the following. Let's choose one domino uniformly at random. One of these domino configurations uniformly at random. So let's try to imagine how can we do that. Okay. So let's try to think in a sort of algorithmic way. Okay, so how do we choose one of these configurations uniformly at random? Okay, so one way to do that, which is probably the first that you may think about, is okay. Let's make a list of all possible configurations. Let's associate a number to each one of them, and now we choose a number uniformly at random, and we look at the corresponding domino configuration. Okay? So this is hopeless, actually, because, so let me see here. So how many of these configurations are? Okay. So in how many ways I can put these 32 dominoes in such a way that they cover the square? This is sometimes it's called the matching problem. Okay. So this is this graph here. You can think about this square as a bipartite graph. So a bipartite graph is a graph that can be divided into independent subgraphs. Okay, so a subgraph of a given graph is independent if there are no edges between members of the subgraph. So here this is a bipartite graph because you can divide it into independent parts. No, you can just color like in the checkboard. The white squares and the black squares, they are both independent subsets of the graph because there are no neighbors. No. So here we're thinking about neighbors if they share. Two squares are neighbors if they share an edge and a side. Okay? So how many of these configurations are? Okay? Of course, it's not 32 factorial or something like that because here we have a structural restriction to what we can do. Okay? But increasingly enough, so let's see if I can find here the exact number because it's a very interesting number. Okay, there is a formula. So let me call it matchings, these configurations. So the number is the following. It's okay, so I'm believing in Gemini, something you should never do. But I'm believing it because I vaguely remember the formula. Okay, and I vaguely remember that the formula was like that. There was some cosine squares. There was a force somewhere. But it's a formula. The point of this formula, which is interesting about this, is that you can check that. So there are n squared terms. So these grow exponentially, like some constant to the n squared. Okay, the constant is around 3 point something, so it's kind of big. Which means that in fact the combinatorial restriction only gives makes a dent, a small dent on the best possible exponential growth that will be 4 in this case. So if you think about it, if you guys like put it in any way, there will be like 4 to n squared. So the point is that this number is very big. Okay, so So Gemini says that for 8 times 8, there are almost 13 millions of ways to do that. Okay? So you can see that the question about choosing one of these configurations uniformly at random cannot be done in a naive way, because you cannot just number all of them, associate you order them, you associate a number, and then you just choose one number uniformly at random. Okay. Now the second question, of course, is why. Why should we care about this problem? Okay. As usual, there are two answers for that one, no? The physicist answer and the mathematician answer. Okay, the mathematician answer is already written in the blackboard, no? Because, well, you know, super fun, no? Look at this formula, no? Amazing. There should be a lot of mathematical fun embedded in this problem. And it is true, okay? So this is an example of what nowadays is called determinantal process. And determinantal processes are random processes, no, random variables, random objects on which the probability distributions can be expressed in terms of determinants. Okay. And then we go to the physicist answer, which is actually related to the mathematician answer, because nice object has a tendency to appear in real life. Whenever you have a nice mathematical object, it has a way to go into the real life in some way, at least. Okay, so what is this? Okay, so you probably know what is the formula of salt, no? It's one atom of sodium, one atom of chlorine, right? So I don't know if you have heard of seen this before, but salt in its usual way, no, in the table salt, in what we find in the kitchen when we used has a crystalline structure. No? It's a crystal. And what type of crystal is just the simplest of all. No, it's just a lattice. It's just and it's exactly a checkboard lattice, right? Because there is one. It's three-dimensional, but in 3 dimensions you can also color. No, black and white. The lattice like the checkboard. No, by parity. No. The sides of the three-dimensional lattice, they have coordinates which are integer numbers. Then you sum these integer numbers. If the sum is even, you color it white. If the sum is odd, you color it black, and you get also a partition of the three-dimensional lattice into 2 independent sets. And one of the sets is sodium, and the other independent set is chlorine. Okay. So now let us imagine that we are looking at a crystal of salt, and for some reason we remember, because for example, if salt is in a different form, it's let's say liquid form. Yeah, that could be a thing. You can heat salt. It's difficult because the melting point is very high, but maybe this is something one can do. Maybe with another type of material. And when salt is in liquid state and it's cooled again to become a solid, what happens in the liquid state is that the atoms, they are form these molecules, no, of two atoms, no, of sodium and chlorine, and they are separated and doing their liquid thing. Okay. And when they go to the solid state, they become this crystal. And maybe, for some reason, you may or may not remember. No? Let's think, ideally, we remember which atom was tied to which one in its liquid state. Okay? So let us think a moment like that. As a theoretical physicist, you can think about that, no? And then just by the laws of thermodynamics, it's very natural. You can even try to prove it, because that's not the point. It's very natural to assume that this configuration of these matchings, no, are chosen uniformly at random, because they were formed uniformly at random. When the salt went from liquid to solid, it did it in some random way. I mean, there is a thermodynamic equilibrium, and though there's no preference for nothing. Okay, so somehow taking one matching uniformly at random, in a sense, is to try to remember how the crystal was formed. Okay, so what physicists they say is that this model here should describe or should help at least to understand the liquid-solid phase transition. Okay, so features that you can learn about this random matching here are things that might have relevance on this problem of the liquid-solid phase transition. Okay. So I'm going to draw another. I'm going to make another drawing here. I will see if I succeed to do it. It's more complicated, so I'm not very optimistic about it, but I will try. If I'm not wrong, I divided this in 16. So when I was at university, at the end of a course, the student had to fill a survey, no, where they kind of evaluate their professors, no? And one of the questions was always, did the professor make use of audiovisual resources? So I hope that my drawings qualify as audiovisual resources. So what I'm drawing here is something that is called in the literature the Aztec diamond. For reasons that are only, of course, known to the mathematician that drew these things for the first time. Well, after drawing a few steps of the Aztec diamond, I think that you start to understand what this Aztec diamond is. Huh? Well, as you can see, you can go home and have infinite fun drawing Aztec diamonds. So you can do this as a sort of meditation, because as you can see, we need a lot of patience to do this, no? Well, it seems that it's a nice one. So let me try. Let me do the same thing I did there with the dominoes here in the Aztec diamond. Okay. So I'm going to fill the Aztec diamond with dominoes. Okay. Okay. So the first thing I'm going to do is that I'm going to do. Okay. Let's do it. Let's put this one here. So now the geometry is a little bit different. So when I put this here, this forces me to do this. Okay, so maybe I won't do it again, no, because it's forced me to do a lot of things. So okay, so I will put one like that. Let's put one like this. Oh, okay, again, I have to. So maybe I do this, and then I do this, and I do like this and like this. And maybe I do here like this, and then I'm forced to do it here like this. Maybe I'll do here something else. Maybe I'll do it here like this. If I do this, okay, now I have to. I created an avalanche here. As you can see in this one, the avalanches that you create when you put a domino are much bigger. Hopefully I'm not doing any mistakes, because as you can see, drawing a new Aztec diamond will take me the rest of the. So this is the Aztec diamond. So let me do the following thing, okay? I'm going to start, I'm going to enter from here, and I'm going to draw a path that is going to follow the direction of the dominoes. Okay, so it means that here it goes like this, here it goes down, huh? So I'm following the direction of the dominoes. Did I did it correctly? Yeah, probably. So what do you, is there something that piqued your attention when I did this? something that might be interesting? No. Huh? Okay, so the thing that should pique your attention is that I start and end it at the same row. That's kind of curious. So let's do it again. Let me start from here now.
So I guess you're following the rule that you never go back. Is that it?
Huh?
You're following the rule that you never go back, because otherwise you could have gone back in the last step, right? You didn't need to go out.
Ah, yes, never come back. Ah, see. So I think I made a mistake somewhere. Okay, let me see. Ah, no, it's okay. Huh? É.
Poderia subir com azul em algum momento, se quiser?
Poderia. Ah, sim, agora lembrei. So, now what we are going to do is that we are going to do the same, but starting from here. Okay? So we do the same starting from here. So you see, I always go, I follow the red line, and then I go to the right. That's the rule.
Então não poderia subir com azul.
Poderia.
Mas se sempre para a direita, isso é uma escolha arbitrária.
Hã?
Mas você está falando que é sempre para a direita.
Sim, mas
Então não
pode.
pode subir.
Ah, não, com azul não.
Ah, tá. Obrigado.
So we do the same again. Podría no preencher. Okay, so this is the Aztec diamond. So the first curiosity is that if you start from here, you always end up at the same point, at the same row where you started. The other curiosity is that all these paths are non-intersecting. They never intersect. Another curiosity, you can here you can actually compute that number. It's an easy exercise. It's just an induction. It's like it has to be a clever induction. It's not immediate, but it's just an induction, and you will see something like 2 to the n minus 1, the number of configurations that you can have. So they also grow exponentially with n. Maybe it's n squared. I don't know. I don't remember. Maybe it's 2 to the n minus 1 divided by 2 minus 1. Something like that. It doesn't matter. You can compute it. Okay? And there is some induction to be done. So the thing, and this is if you looked at maybe you look at Levin WILMER book. In the front page, there is a picture of one of these things for a very, very big square. And what you see in that very, very big square is that this curve here, the lower one, converges to a circle, which is called the Arctic circle. Okay, so if you take a very, very big square, this curve here, no, will converge to the circle which is tangent to the side. So the center of the circle is here, no? The radius is, if you normalize to 1, it's 1. No? It's the side of the square. And what happens below this random line here, in a sense, is not very interesting, no? Because what you see is that all dominoes are horizontal below this line here. So this line here separates the order phase to the disorder phase. Okay, so here things are disordered, more or less, and here things are the dominoes are very ordered in the fact that they're all horizontal. And here, if you look at a point inside this region here, what you will see is that you don't know. Okay, it could be horizontal, it could be vertical. The probability is more or less 1/2, 1/2. You look at a point here, whatever point here, and you ask the question whether the domino that is covering this point is horizontal or vertical, and this is going to be more or less 1/2, 1/2. So this is called the Antarctic polar circle theorem. Well, actually, the theorem is called the Arctic polar circle, and it's done the other way around. But since we are in the south hemisphere, we do the Antarctic. Okay, so in case you want to search it on Google. So now things are getting more interesting from the point of view of physics, because it is true that in this very simple model, when you take a very big box, in this case a very big square, what you see is an ordered phase and a disordered phase. So this region here is what people call the solid state, and this is the liquid state. So effectively, looking at this very simple model, you start to see a little bit you start to see features that are reminiscent of the original problem. So this is what is very interesting about mathematical physics. Okay, so first you cook up a model which may or may not be justified, no? Because of course a very important modification I did to this problem, coming from the problem in physics, is that I'm drawing two-dimensional pictures and not three-dimensional pictures. No, so if we were really sticking in very strictly to the physicist to the physical meaning of the model, we should have gone only to 3 dimensions. But what happens is that 2 dimensions is solvable. Okay, we can do things, and in 3 dimensions you cannot. So let's stick to 2 dimensions and see what happens. And then you go, no. Then it's a well-defined mathematical problem. For a well-defined mathematical problem, you can actually try to prove things. And this is one possible theorem. So the Antarctic polar circle theorem, that tells you that the region that there is an order phase and disorder phase, and the region that separates both, it's a circle. Okay, so the precise description of what happens in general domains for this is due to Algum. And it uses algebraic geometry. And as you may know, whenever you use algebraic geometry for something, you get a Fields medal. And so in particular, Algum got a Fields medal for this work. Okay, so this is just to show you that this model is nice, is very beautiful. But then we can go back to the original question. Which is okay. So this is nice, beautiful, etc. But maybe this is too mathematical, no? Maybe we want to do the three-dimensional case. In the three-dimensional case, we cannot do exact computations. There is not a super fancy Aztec diamond graph on which you can do exact computations and get deep results. So what do we do? And physicists know what to do. They just do that. Well, then we run simulations. And if you want to run a simulation, you want to cook up a way to choose one of these configurations uniformly at random. But this is a difficult problem, because how do you with a list? I mean, we already seen that if you want to make a list, it's too big. Now, if you try to make it at random somehow or with some algorithm, we have already seen that it's not clear at all that we can do it in such a way that the result is chosen uniformly at random. No, because okay, the first one that I'm going to put here, it should be go this way and this way. That's okay. But then after that, the next one, how do we choose the next one? At random, but at random how? No, there are, for the second one, if I wanted to put it adjacent to the first one, there are 1, 2, 3, 4, 5, 6 possibilities. Some of these possibilities automatically lock the problem, so you have to put additional dominoes because you are in places on which you are forced to do it. Some other choices don't. Should that impact my choice? How? Even if it's not the case, why should it be uniform? I mean, how do you choose? In such a way that at the end, when you construct the whole thing, you get a uniform configuration. Okay? In fact, this idea of paths that go to the other side in a non-intersecting way hints at maybe how to do it. No? There is some combinatorics about non-intersecting paths that you can use, but if you want to go to 3 dimensions, you are doomed. No? This is not going to work. Okay? So how do we do it? And this is where the first MCMC will appear. Okay, the first, it's probably, it's not exactly historically accurate what I'm going to say, but it's morally accurate because it's for similar type of problems that physicists actually invented MCMC. And the thing is, okay, let's do the following. Let us invent a Markov chain such that the invariant measure of the Markov chain is a uniform distribution on domino tilings. It's the uniform distribution on matchings. So how can, so before thinking about inventing a Markov chain that makes this, that has the uniform measure as an invariant measure, let's try to do something simpler. Let's try to invent a Markov chain. Okay? So how can we make, what will be a jump here? I mean, what can be a jump? Okay? So actually, if you think a little bit about it, the most the simplest thing that you can imagine is that, well, let's try to rearrange these dominoes in a simple way. Okay? So what can we do? Okay, so I just want to make a change on this configuration, the smallest possible change in such a way that I get a new domino tiling, a new matching. So, well, here you see, in this square here, I can do a very simple thing, which is just, I can just rotate the dominoes. And that will give me a new matching configuration, which in a simple way. So, okay. I can do that here, 4, 5, 6, 7, 8. I have 8 squares on which I can do this exchange of orientation. Well, I can do, so which one? So among these 8 squares, which one should I choose? Well, here there is an opportunity to make a Markov chain, no? Let's do it at random. And how at random? Uniformly at random, because, I mean, if we don't have any other choice, uniform is always the best one. So, without a reason to do it in a different way, uniform, okay? So that defines a Markov chain, okay? So we start with this one, and we choose one of these squares uniformly at random. One of the 2 by 2 squares formed by the 2 dominoes. And what we do is that we flip. So let us try to see if this chain is, the chain I just defined is irreducible. We have to do all the mathematical thing, no? So we have to, we just define a Markov chain, and we want to look at this at the invariant measure. So if you want to look at the invariant measure, the first thing that we have to do is to check whether the chain is irreducible or not, because if it's not irreducible, it will have more than one invariant measure. Or maybe it will get stuck somewhere, no? I mean, it's not going to sample what we want. Okay, that is complicated, okay? It's difficult to see if this chain is irreducible or not, okay? If you think about it, there is a complicated way, maybe. I mean, let's try to put everything horizontal, because if we can pick any configuration and put it horizontal, then we can undo and get from any configuration to any other configuration, and then it will be irreducible. So if you want to get everything horizontal, maybe you start somewhere, no? Here is not good, because you see this one is vertical. It's complicated, you see, because this one is vertical. If you want to put this horizontal, I have to first flip these 2 horizontals to vertical, and then I have 2 verticals here. I can flip them to horizontal. So you can check it by induction. It's a complicated induction because it's a double induction, no? in the length and in the height of the rectangles. Because you can check that if you can put this row horizontal, then this one up. So induction step, probably is okay. But the induction step, you have to do a square. It's complicated, okay? But it can be done. It's not that difficult, but it requires some work. Let's check the Aztec diamond, okay? In the Aztec diamond, since I drew these paths here, there is an easier way. Because let's look at the lowest path. The lowest path has here a minimum. This minimum is the first vertical. It has to be a square, so I can flip it. If I flip this, the path goes straight here. So the path goes one step up. And actually, this is something I can do at every minimum. So I now went one step up. So these two are like this now. And now these two are like this. So I can flip it again. Now I get two minima and do it. So okay, I can always go, if there is room between the lowest one and the next one, I can always lift the lowest one until there is no room with the next one. Then I go and look at the following place on which there is room. In this particular one, there is no room anywhere, no? By some coincidence. So I go here up, and I do pluff. I flip these ones. Now I get horizontal. I get room here. I got room here. I can lift this one up, and I can do it layer by layer. So maybe it's easier to start with the last one. So let me explain the argument again, but starting from the upper one. So this upper one here, I can put it straight by flipping this one. Pliff. Now it's straight. Good, horizontal. Let's go to the next one. One can check that you can do it, no? Because first you flip these ones to get two minima here, and now that you have two minima, single minima, ploof, ploof, and go straight again. You know, then to the next one, do the same again, and there is some algorithm. This algorithm actually can also be found here, okay? And I'm going to show you that it can be found here just doing a picture, okay? Sorry. This is not what I wanted to do because this is correct. I made a mistake here. Yeah, this is a mistake. Okay, sorry about that. You always go to the right.
Sai sempre do mesmo lugar também, nesse caso?
Vamos ver.
Porque ali dentro tem, né?
Mas aqui eu tenho que começar saltando um. So here it happens the same, but if you wanted this path to be non-intersecting, you have to leave one of room. Yes, okay, yeah. So you can see that here, you can do the same algorithm. You straight the first line, then you straight the second line. It's not completely immediate because here you have to strike this first and then the next one, but you can implement a similar strategy. Okay, you go straighten out the lines from. And And you can show that this chain is actually reducible. Okay? Okay, the chain is irreducible. Is it reversible or not? So what is the easiest way on which... Okay, so there is a theorem about it, no? If a chain has the uniform measure as invariant measure, it is... reversible if and only if it is the transition probability matrix is symmetric. Okay, so let's check here if the transition matrix is symmetric or not. Okay, so when you flip here, so we have, I told you that we have 8 possibilities, but when you flip here and put it horizontal, now I have an extra possibility. I have 9 possibilities. So it's not going to be the uniform measure is not going to be invariant because of this detail, no, that sometimes I get an extra square, and if I get an extra square, then the probability of coming back is not the same, no, because it's going to be 1/9 instead of 1/8. Okay, so we need to do something else. Okay, so we need to choose the squares in such a way that choosing. So the idea, the easiest way to check whether a certain invariant measure is invariant is to check it if it's reversible. Okay, because you don't have to check all these complicated equations. You just need to check whether the probability of going is the same as the probability of coming back. So now, how do we modify these dynamics here in such a way that the probability of reversing the move that I did in my previous step is the same? Okay? And the answer actually is very simple, is that we can lose a little bit of tries. Okay, so let's say that instead of choosing one of the 8 squares uniformly at random, we choose any square uniformly at random. For example, I choose that one. That one cannot be flipped because this 2 by 2 square is not formed by 2 dominoes, no? There are 1 domino here, here, so 3 dominoes are covering that square. So if I do that, and I choose a square that I cannot move, I just simply don't move. But if I choose a square that I can move, then I move it. There are 1, 2, 3, 4, 5, 6, 7. So n minus 1 times n minus 1 of such 2 by 2 squares. I choose one of them uniformly at random, so the probability is 1 over n minus 1 to the square. And the probability of reversing the step I did in the previous step on the next step is the same. It's again 1 divided by n minus 1 squared. So in that way I guarantee that the invariant measure is uniform. So random algorithm. So step 1. So step A, let's say. So choose a 2 by 2 square uniformly at random. I should have invented this thing before, no? Uniformly at random. Yeah, I would have saved like from the beginning of the course like half an hour. If formed by 2 dominoes Dominoes. For some reason, the plural of dominoes is with E, no? Formed by two dominoes. Huh?
Se não vira pizzaria.
Se não vira pizzaria, exatamente. Then flip them. By flip them, I mean just change the orientation, no? From horizontal to vertical, or from vertical to horizontal. And see. Otherwise, do nothing. So this is the algorithm. There is a small problem with this algorithm, which is it's not lazy. Okay, so maybe it's better to flip them with probability 1/2. Okay, maybe not. I'm not sure.
The whole thing is staying there anyway.
The whole thing stay there, but not always, because all dominoes are horizontal, you don't stay there. Or all dominoes are vertical, you don't stay there. So one has to realize whether this modifies things or not. Periodical, yes, because I need only one configuration with a loop to make it a periodic. Okay, so you don't need to do it like this. Well, you may or may not need it, okay? Because the nice thing about there are more things nice about lazy random walks than just this irreducible thing. Another thing which is nice about lazy random walks is that all eigenvalues have positive real part. So imagine this problem. I don't know if you did that problem in the exam about computing the eigenvalue and the eigennumbers and eigenvalues of the random walk on the hypercube. So it was lazy, the random walk. That was important because then all the eigenvalues were positive. If they were not positive, the computation will be a mess, because then you will have all this 1 minus 1 to some powers around in your computations, making a lot of noise on the thing. Okay, so for spectral reasons, it's nice to consider lazy random walks because all the eigenvalues then are have positive real part. That has other implications, no? Not only from the point of view. So yeah, from the point of view of when you do algorithms, you want to avoid the most you can these kind of oscillating things, because algorithms, they don't like oscillating things. So what happens with this is that this creates a Markov chain on the space of domino tilings of the square. Why is that interesting? Because now we can do this. We can say the following: how do we sample? How we do choose? It's the same thing. One of these configurations uniformly at random. We run this Markov chain until the mixing time, and then with some epsilon precision, we have a uniformly chosen random domino tiling of the square. And here, so the thing is that this is very interesting, because the other alternative that I can imagine, which is just making a list and choosing one of the elements of the list that is uniformly at random, is completely out of question. It's completely hopeless. This one So it was shown that the mixing time is at most of order n to the quarter, n to the fourth. Okay? So Wilson, I think Wilson proved that. So it's the same of the Wilson method that I mentioned before, and it's actually on the same paper, because in the paper on which he introduced this Wilson method, he considered various different chains that he shows because he knew they were difficult. I mean, they were doing difficult problems on this one of the chains, and he showed that a lower bound of that the mixing time is at least n squared. N squared is in this case here is more or less obvious that n squared has to be the it's a lower bound for the mixing time, because n squared is the least something that is more or less obvious. Is you have to choose every square at least once, because if you haven't choose one square at least once, then there is no chance that you are close to uniform, because that square has the original orientation. Okay, so you have to choose every square at least once. So n squared is more or less obvious. He got a lower bound of order n squared log n, and he argued that that was the right order. I think this problem is still open. I don't remember. I haven't checked the literature enough for a while, so I don't remember if it's this is updated or not. I think that the best upper bound is n to the third. But these guys are clever, so there is a clever modification of this algorithm that whenever you choose a point like this as what you do, instead of updating a square, you update a region around this point. No, it's like you find a region that you can update, and then you can modify, and then you modify it. So you do it in a clever way, you get an algorithm that actually has a n squared speed of convergence, which is, well, there is some log, n squared log n, which is the best possible. Anyway, n to the 4 is already good enough because it's polynomial. So the idea is that my previous algorithm of listing all the configurations and just picking one of them uniformly at random has an exponential running time. But this algorithm is polynomial, has a polynomial running time, so it's way better. I mean, and I don't know, maybe you can find another way to do it, but at least for me, I don't see any other way to solve this problem besides these two, no? Markov chain Monte Carlo and brute force naive listing. So this is the first example of a Markov chain Monte Carlo algorithm, and the idea of Markov chain Monte Carlo is exactly that. So I want to simulate, I want to sample some given distribution, okay? And this given distribution can be difficult to sample for from different reasons, because, for example, I don't really know it. Because in this particular case, the difficulty comes from the geometry of the space. No, that is the simplest of distributions. It's the uniform distribution, but the problem is the geometry of the space on which this uniform distribution is living, which makes the problem complicated again. Sometimes the geometry is easy, but the measure is difficult. And In this problem, the physicists also proposed a modification that takes into account gravity. So they say, okay, we can also, instead of making uniform, we give weight, different weights. So let's say we give weight 1 to the horizontals and weight Q, which is the usual letter they use for these things, to the vertical ones. Okay. So you imagine that if this thing is being created by random deposition, so there is a substrate. There is what we usually is called a super how? It's super cooled liquid, not really super cooled liquid, super saturated liquid. So you have a liquid which should be a solid, but it's not solid because you did something. There is this funny trick that you can do with water. No, you can put water on the fridge, cool it below the freezing point. Take it with very care, very slowly out, and then pour it very quickly into some recipe. And what is going to happen is that it is going to freeze while it's falling. It's super fun to do. You can do it at home. It's actually a nice thing to do on summer in Rio, because then you get really refreshing liquid. No, actually. Frozen liquid, no? So so this is super saturated, and you can do that to actually grow crystals. This is a way to grow crystals. So because you take a super saturated liquid, then you do something at the bottom, some small perturbation, and a crystal starts to grow from the bottom. And if you do it in a controlled way, you can grow crystals in very precise ways. Yeah, some time ago they did chips this way, but I think now they are super sophisticated. They just cut it with a knife, no? Because they have this super precise knife that they can cut slices of 10 atoms, no?
Wow.
Whatever. But it's something you do. So you grow this crystal, and since there is a direction of growth, there is gravity. You usually think about this as not having the same probabilities, no? Because it's more likely to put an horizontal domino than to put a vertical domino, because these dominoes are slowly falling down. But you can do that. It's very easy, no? This is something we can explain later, but the point is that you can easily modify this algorithm here to get different probability distributions, and this is one of the big things about Markov chain Monte Carlo. That once you get an algorithm to sample the uniform distribution, you can modify it to sample other distributions. This is what is called the Metropolis Hastings algorithm, but this is something that we're going to explain in more detail tomorrow. Okay? So we can do this, and this algorithm is super fast in the sense that it's polynomial. It's polynomial, and even with a small polynomial exponent. I mean, it's proven that it's polynomial. It's believed to be polynomial. It's believed to be n squared log n, which is the best possible. Yeah, just because you cannot do better than squared log n, because you have to at least update all the squares once. Okay, so So let me describe now what is the sampling problem. Okay. So the idea is that we have function random, okay? That samples IID let's say this, okay? So it samples IID realization of a uniform random variable on 2 to the n, okay? So people usually at this point, it depends a little bit on what you want to draw. You can imagine that you have a random function that samples a uniform 0, 1. Okay, but this is not exactly realistic. There is this. I'm not completely sure if this statement is rigorously true. It's something that a colleague in applied math once told me. Is that if you have actually a true random generating function, if you have this uniform 0, 1, then you can simulate a quantum computer. Okay, so it means that a quantum computer is at most as powerful as a random generating number. I mean, at a random number generating function. Okay, so which means that in a sense all this fuss about quantum computing, it's a little bit it's slightly exaggerated in the sense that well, if you're good at random algorithms, you can forget about quantum computing because you can just use the quantum computer to generate random numbers and then do it classically. But this is what we assume, no? Whether this is reasonable or not is another question. So usually the numbers that a computer generates, these random numbers that computer generate, are pseudo-random numbers. Okay, are numbers that they pass most common statistical tests, but they are not really random because you don't really have a way to generate random numbers on a computer. Huh? They are not IID. So so this is a big assumption. If you are doing really serious computer science, this is something you have to worry about. Okay. But if not, it's not that you're not doing really serious, but it's you have to understand how many times you can use your random generating function before these pseudo-random numbers start to become deterministic, no? But in our problem, we are going to assume that we have this. Okay. Of course, all this discussion was only to tell you that I'm going to do this at the end of the day. Okay, so I'm going to assume that my random numbers are uniform 0, 1 because I don't want to be so picky. So what we want to do is we want to simulate So this is a sampling problem. So, as usual, we start with the simplest one and then start to do more complicated things. Okay, so let's say case 1. Mu is it's a law. Remember that law is just the same thing as probability distribution. Okay, I use law instead of probability distribution because in my line of work we also use temperate distribution, the distributions that come from PDEs. So, and as I told you, these mathematicians they ruined all the words and letters by giving the same name to two different things, or giving two different names to the same thing. So mu is a law on R. Okay? So I have uniform random variables and I want to simulate, let's say, the Gaussian. Okay? Or the exponential. Geometric. Geometric is also a law on R. No, it's a law on the non-negative integers, but the non-negative integers is a subset of the real numbers. So, and we want to simulate this. Okay. So how do we do it? So we use something that is called the generalized inverse. Okay, so the generalized inverse is better to describe it using a picture. Okay, so So what I drew here is just the what is this? Is the probability distribution function of the law mu. Okay, so you take a random variable x with law mu, and the function f mu of x is just the probability of x being smaller or equal than little x. Okay. So this is the probability distribution function of our favorite probability law. Okay. So how do we use uniform random variables to sample mu? So what we do is that we observe that here there is a uniform, there is an interval 0, 1. So we throw a point here, uniformly at random, and we convert this point if this is if this is u1, let's say, I define x1 here. Okay. So maybe now I throw another uniform random variable u2, but now, so here there is a jump on the probability distribution function. What does it mean, a jump on the probability distribution function? It means that this value here has positive probability. So how this positive probability reflects into this thing I'm doing here. So here what I'm doing is just I'm taking the inverse value of this u1 by f. So doing this is taking the inverse function of f. So this x1 here is f minus 1 mu of u1. But here is a little bit different, no? Because it's not the inverse. Because actually, all this interval here is not in the domain of the inverse, because it's not in the image of the function f. But you see that if I drew this line here, and I do this, pop, 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 the probability of hitting here is exactly the length of this interval, which is exactly the probability I wanted to simulate. So this one here is u2, and u2 is actually equal to something different, no? Is sorry, yeah, x2. Yeah, thank you. So we put a tilde here, because you see all this interval goes to this point here. And this point here is defined in the following way. So you have to think about it, how to define properly this inverse here. Is what we call the generalized inverse, and it's defined in the following way. So the formula of this generalized inverse, it's only important, usually it's important for mathematicians, not for not in general, for the general public, but is the infimum of this. Okay. So here I warned you that the probability of this formula being correct is a little bit higher than 1/4. Okay, because I could make a mistake here putting an infimum instead of a supremum, making a mistake here on putting a bigger than equal instead of a bigger than. Okay. So, well, but in the book there is a formula which is correct because it was checked more than 4 times. But the idea is that if you have a point here on which the function f is continuous and instead of increasing, this is exactly the inverse, just by continuity. Okay. But in this region here, what happens is that you have to make a decision of what are you going to put as a generalized inverse, which doesn't really matter, because the probability of hitting exactly this line is 0 when you throw a uniform here. And in this part here is where it's important to make the right choice, no? Because you want to choose this point here whenever you fall in this interval here. Okay? So, and the idea is that this x here has a low mu. Why? Because the probability of xi being smaller or equal than x and so the idea is that the generalized inverse is whatever function I had to put here in such a way that the next step on this computation is correct. So now I can apply the function f on this inequality on both sides. So if I apply f on both sides, here I get the identity, and here I get f of x. And now, what is the probability of a uniform being smaller than some number? It's just the number, because it's uniform. No, it's uniform 0, 1. So this is exactly equal to f mu of x, which is what we actually wanted. Okay? There are some, so this is basically the proof. There are some small details. So, for example, this inequality is true only at points of continuity of x, of f, which is okay, because that's enough to make the distribution function well defined. But the point is that using this function, which is the generalized inverse of the probability distribution function, we can generate this sequence now is IID with log mu. Okay? So if we have a law on R, we can use uniform random variables to generate it in this way here. Okay? An observation, okay, which is it is of some it is of somehow of interest in this business of random sampling is the following. So if So if I have IID random variables with lower nulli, then this random variable here has low uniform interval of 0, 1. How do we interpret this? It's very simple. This is just the binary expansion of a number between 0 and 1. So if I have a sequence of IID zeros and ones, I can write this number as the binary expansion of a number between 0 and 1, and this number then is chosen uniformly at random. And this is goes both ways. If you take a number which is a uniform 0, 1, then looking at its binary expansion, we get a sequence of IID coin tosses. No? So we get a sequence of IID diver nullis parameter 1/2. So from this you see that having a uniform random variable gives you, in a sense, infinite randomness. Because if you have one uniform random variable, when you have one uniform random variable, you can extract from it an infinite number of coin tosses. And doing this trick of taking of dividing Z into infinite subsets of infinite length, now you can extract an infinite array of coin tosses. And each row of the array you can transform into a uniform random variable. So actually on a uniform random variable there is the same amount of randomness that's on an infinite sequence of uniform random variables. Because there is actually a measurable map from the interval 0, 1 to the infinite cube. And what is the map? You just take the binary sequence and then you divide this binary sequence into infinite number of binary sequences. Okay, and you do the usual thing. No, you take the odd numbers, then the numbers equal to 2 modulo 4, then the numbers equals to 2 modulo 2 modulo 4. Then you take equal to 4 modulo 8, equals to 8 modulo 16, and in general equals to 2 to the n minus 1 modulo 2 to the n. No? That's the classical way to divide an infinite sequence into an infinite sequence of sequences. Infinite sequence of infinite sequences. Okay, so just to tell you that actually uniform has too much information. So that is one more reason why it's always good to have in mind that we don't really can hope to sample uniform random variables in the whole interval 0, 1, but on a discretization of the interval 0, 1. Okay, so now let's do another example. So this one is the integration problem that I mentioned to you before. Okay. So how this integration problem goes? So you have a domain, and I want to choose a point uniformly at random inside this domain. Okay, using uniform 0, 1 IID random variables. Okay, so this is the domain D. So we are going to assume that this domain is bounded. Okay. Otherwise, what I'm going to do doesn't work, but then you can modify to your convenience whatever we are going to do. Okay, so I want to choose a point inside here chosen uniformly at random. Okay, so this uniformly at random I should start to write like this, no? Much easier. UAR. So how do we choose a point inside here uniformly at random using 1, 0 random variables? So now it's a two-dimensional problem, so that thing there doesn't work. So you see, this is clearly a mathematician. So what does it mean uniformly at random here? So what I imagine is that this set D here is embedded in R2, and then I'm thinking about the usual Lebesgue measure in R2. Okay, so so the usual area measure. If you don't want to go to Lebesgue, and you area measure, this is still okay because this is a nice domain. So you can compute the area of this domain. No? It's some number, and now you can see that the probability of choosing a point in a region here is just the area of the region divided by the area of the domain. Okay, so for every A containing D, the probability of X belong to A is just the volume of A divided by the volume of D. Okay, so we want to compute a random variable with this law here. Okay, and here I have to make some assumption of A so I can compute the area. No, so let's say that it's a ball. Usually domains are like that. No, domains are open. No. In PDEs, at least, when you say the word domain, it means open and hopefully bounded set. Because it has to be open because you have to be able to take derivatives. And if you want to take the derivative of a function, it has to be defined in an open set because you need to say what does it mean a neighborhood. So here, when I do this definition here, this A usually is a ball. Because this domain maybe is bounded and open. Okay. So this is what it means uniformly at random. It means that we are using the area to define the probability distribution of a point inside D. Okay, so how can we do this? So the keyword here is bounded, okay? Because if it's bounded, I can put it inside the rectangle. And now what I'm going to do is that I'm going to choose a point here uniformly at random and a point here below uniformly at random. This is something I can do because, okay, maybe the length of this the sides of this rectangle are not exactly equal to 1, especially because it's a rectangle, not a square. But you can always normalize, right? So
O domínio está fora da figura, né? Digamos.
essa é o domínio é a figura.
Ah, tá.
Então, o D estaria dentro, talvez. Então, so in this case, what I did is that I choose. Okay, it was bad luck. So the point is outside. Well, if it's outside, I do it again. Okay. And as you might imagine, now that I'm doing it again, I'm going to be lucky. Of course, just for pedagogical reasons, the first time you are unlucky and the second time you're lucky. And now you get a point inside. So the claim is the first time that you get a point inside, you get a sample of X. And this is actually true because when I say ball here, I still have the right to choose the norm, no? So here, the norm that is well suited for my purposes is the supremum norm, no? The maximum norm. Because in the supremum norm, the balls are squares. And for a square, it's obvious that this is actually the probability of hitting a square inside D. Okay? So it was a nice picture, no?
You're gonna get all the points in the audio visual. Your visual level.
Exactly. So, so the algorithm now is go like this, no? So I hope you find it reasonable, this, okay? That we just throw points uniformly at random on the rectangle, and the first time I hit inside D, I get some point chosen uniformly at random inside D. Okay? You can put you can prove it, no? But it's a reasonable thing. So put D inside a rectangle. R equals A1, B2. B. Define xi is going to be equal to A1 plus U2i divided by A2 minus A1, comma B1 plus U2i plus 1 divided by B2 minus B1. No, sorry. It's not divided, it's multiplied. Okay, so this is the actual definition. No? If you really want to code this idea of taking 2 points and choosing like this, you have to do this kind of weird thing that okay. So if the sample is already given to you, you have to use one guy for one coordinate, the next one for the other coordinate, and then you burn 2 of your random numbers, so You have to put a 2 here, so in the next step you take new random numbers. But otherwise you can do, if you don't like this, no, it's easier to code it like this, no? Okay? But anyway, you define these numbers here. These numbers are random in the square. And in general, you define n L, or n of t, in an inductive way, no? So we are already defining n1, and now we can define nt. And then we define zt as x of nt. So we wait until the first time we hit inside D, and that is going to be x1. And if we want a sequence, what we do is that we run the algorithm again, no? We run the algorithm again, and we wait until the second time we hit inside D, and then it's going to be Z2. And so on and so forth. Okay? So, in this way, we have defined a uniform measure inside the set D. So this random algorithm is an example of a rejection sampling algorithm. So what does it mean, a rejection sampling algorithm? Well, there is a first step, which is a sort of easy step. So we sample a random variable, which may or may not be good for what we want to do. Then we do something with this random variable. And when did we take a decision whether we keep it or we reject it? Okay, so the rejection algorithm here is, if it does not belong to D, then we reject the sample, and if it belongs to D, then we accept the sample. Okay, so this is a first example of rejection sampling. It's a simple instance of a rejection sampling algorithm. Okay. Well, I think my time is off. We stop for today. So we see you tomorrow. So what I did today are actually building blocks of what we are going to do tomorrow, which is the Metropolis Hastings algorithm.